All right. Hello, everybody. This is Miss Pie. I am at the dentist's office getting some dental work done again. And hopefully, you will be nice and respectful to the sub. And I will see you guys on Tuesday. So, for this video, make sure you have your worksheets or the pages out of your textbook. I think they're page 411 to 414. And I'm going to start off this video by showing you a portion of a YouTube video that's titled Cheetahs and then the Deadly Race. We're going to see a part of it. However, there is not going to be any volume because I'm going to talk through the video. Okay, so you see these antelope. I'm not sure exactly what kind of antelope they are. They're just antelope. And those of you that are terrified that I'm going to show you blood and guts of a cheetah killing an antelope, you're not going to see any of it. I stopped the video before that. Those of you disappointed, you can go and watch the video on YouTube on your own. All right. So this video clip, let me go ahead and push play. You have antelope here. You have a cheetah hiding out in this brush here. And I just want to, I'll start it and then I'm going to stop it in a little bit. Okay, so here's the cheetah. She's running out of that brush and she's running towards all the antelope. And she's running. Sorry. It's not nearly as climatic with no volume. Sorry, guys. And she's still running. Now, you guys all know that the cheetah is the fastest animal in the world. So she should be able to catch the antelope with no problems, right? Let's see what happens. Okay, let me pause this for here, right here. I want to point some stuff out to you. So first of all, you've got the cheetah. She's running. She's right here and she's running. I know she's kind of blurry. Sorry about that, guys. But she's going to try to catch some of these antelope. Okay? And let's say she's going to run this way. Okay? The only way she's going to be able to catch any of these antelope, let's pick this antelope. The only way she'll be able to catch this antelope is if this antelope also runs this way, and if both this cheetah and this antelope get to this spot at the same time. Okay? So in this scenario, there's three different possible options if they're both going to actually run this way. One option is the antelope runs this way and arrives at this spot before the cheetah does, and the antelope is going to just get to this spot and then she's going to keep on going. She's not going to stop and wait for the cheetah to catch up. Okay? If that happens, then the antelope is home free, not going to get eaten. Okay? The other option is that the cheetah gets here to this spot before the antelope. And most of you guys, if you've ever seen a documentary about cheetahs, they run really, really fast in a straight line, but they can't just like turn on a dime and change directions and quickly go after the antelope. If the cheetah gets here and the antelope's not here, she will actually keep on going for a while before she realizes, oh man, I passed the antelope, I have to turn back and come back and get it. Okay? So it takes them a while to, I guess, change their direction. Okay? So that's the second scenario, is that the cheetah passes the spot before the antelope, and again, the antelope's home free. The third option is they both get to this intersection at the same time, and then the cheetah eats the antelope. Okay, so of those three options, only one option allows the cheetah to successfully catch the antelope. All right, so let's go ahead and finish watching a little bit more of the clip. Let me see, when am I stopping it? I'm stopping it at 12:56, or sorry, 14:56. I'm watching the timer. I don't want you guys to see blood and guts and go home with nightmares. Anyway, so you see the cheetah. Cheetah's still running, and you can tell that all these antelope they're not dumb. They are changing their path so that they're out of the path of the cheetah, but the cheetah keeps on going. Maybe the cheetah has her eye on one of these antelope here, but the herd is going to absolutely scatter, and they're going to keep on going, keep running, and running. And the cheetah, of course, is running and running and running, trying to catch the antelope. Okay. And of course, the antelope keep running. I know for some of you, this is very, very entertaining watching animals run. Okay. And you can see that even though the cheetah is the fastest animal in the world, approximately two-thirds of the time that they're chasing after an animal, they don't end up catching it because they don't arrive at the same spot at the same time as the antelope. Okay, in this case, the cheetah did not catch the antelope, and the antelope were able to graze and be free and live another day. All right, that's all I'm going to show you on that video. If you want to see more, you can go on YouTube. This is what the video clip is about. And I will tell you, they have some pretty dramatic sound effects. So you can check it out if you want to. So that's how I'm going to apply this situation to what we're going to be doing in class today. So remember last unit we were talking about vectors, and you had the ship and the pirate ship, and if the pirate ship caught your ship, then the pirates would get all your goods, and you were either killed or set out to sea with no supplies or something like that, okay? So what we're going to be doing in this unit is very similar to what we were doing with our vectors, but we're doing parametric functions, and basically it's just a situation where you have things are moving, two different things or even three different things are moving, and you need to figure out their positions according to time, okay? And so the example in the textbook that we're looking at, you have two ships are sailing in the fog. Both ships are being monitored by the same tracking equipment. So if any of you guys have ever seen any type of movie with submarines or ship vessels or anything like that, they always have a almost like a sonar thing. It's round, and you'll see pixels pinging anytime ships are close together. Okay, so that's what they're talking about on the tracking equipment. As the ships enter the area being monitored, their positions are displayed on the observer's rectangular screen by a brightened point called a pixel. The lighted pixel representing the first ship, the Andor, is at a point 900 millimeters from the bottom left corner of the screen along the lower edge of the screen. The lighted pixel representing the second ship, the Helsinkie, is located 100 millimeters directly above the lower left-hand corner. 1 minute later, the positions have changed. The Andor has moved to a location on the screen that is 3 millimeters west and 2 millimeters north of its previous location. The Helsinkie has moved to a position of 4 millimeters east and 1 millimeter north of where it had been. Assume that the two ships will continue to sail at a constant speed on their respective linear paths. Okay, so notice I've underlined a couple of things. Your initial position up here, this is telling you the initial position of the Andor. This part is telling you the initial position of the Helsinki ship. And then after a minute, this tells you where the Andor has moved, or how far up, down, left, and right the Andor has moved, and how far left, right, up, or down the Helsinki has moved, okay? So then we need to go ahead and start answering the question. So let's look at it. The first one, question 1 says, the grid below represents the area being monitored on the tracking screen graph and label a point to represent the starting location for each fictional ship, Andor and the Helsinki, and sketch the path of each of the ships, excuse me. All right. So on the Andor, it was on the very bottom of the screen at 900 millimeters from your, I guess, bottom left corner. Okay, so if this was a grid here, your y-axis, x-axis, then the Andor would be approximately 900 millimeters right there. And then the Helsinki started just straight up on the left side of the screen, just straight up to 100 millimeters, okay? So this is the starting point for the Helsinki. This is the starting point for the Andor. All right, and then after a minute, the Andor ship has gone to the left. Let me see. The Andor has moved 3 millimeters west and 2 millimeters north. Okay, now notice my point here is actually 300 millimeters and 200 millimeters. The reason why is because I'm not going to sit here and try to find where 3 millimeters west and 2 millimeters north is. It's like crazy trying to figure it out. But I can do 300 and 200. Okay, when I do that, after I do that, I can then draw a line connecting it like this. And because, let me see, where does it say? Because it says that the ships are moving at a constant speed on their linear paths, I know that I'm going to have just a straight line here. And as long as my line intersects this point and this point, it should be straight. So guys, use your student IDs to draw your line there. And then let's look at the Helsinkie ship. Okay, so Helsinkie was here, and then they go 4 millimeters to the right and 1 millimeter north. And again, same thing, I'm not going to draw a point way over here, but I can do 400 millimeters and 100 millimeters up. Okay, so that's your rate of change. And then I can connect my dots, and my line looks like that. Okay. All right, so let's go ahead and look at the next thing. Number 2, to find the coordinates of the point on the grid where the paths cross, you can write functions for the paths of the two ships. What is there about the ship's motion that tells you the paths are linear? We kind of went over that, this constant speed, where it tells you it's a constant speed. That means you're not going to like go one rate and then change, and then maybe go faster, and then maybe go slower. It's not going to have this zigzag thing because it's a constant speed. It's just going to have a line like that. Okay. Let me get rid of all this. All right, so our constant speed, that's why we know it's linear. Yep, the rate of change is a constant. All right, what speeds are represented by the two ships on the tracking screen? Okay, so this, remember when we were doing vectors? Like if we had one vector that went one way and then another vector that went another way, we could form a triangle, and then our resultant would be this thing here, this section here. Okay, if that's our resultant, we would find the formula for this by doing the Pythagorean theorem, the square root of this measurement squared plus this measurement squared. That's how we'd find this length here. Okay, so for the Andor, whoops. That. For the Andor, it's going to be the square root of 2 squared plus 3 squared because we're going, I think we were going up 2 and over 3, or one or the other. It doesn't matter which order these are in. Just the square root of 4 plus 9, which gives us the square root of 13. And remember, we want exact answers. And actually on this one, because it's an application problem, I would be okay if you gave me a rounded decimal, because if somebody said, hey, I want you to go the square root of 13 millimeters per minute, they're going to look at you like you're crazy. If you say, I want you to go about 2.5 millimeters per minute, then they kind of have a better idea. Okay. Now, same thing for the Helsinkie. You do the two portions, the upward movement squared plus the sideways movement squared, and that will give you your speed or your resultant. Hopefully you guys haven't forgotten all that stuff. I know it has been 2 whole days since you worked with vectors. All right, and then so that's how we are getting our speed, and notice it's millimeters per minute. And that's because of the information. Where does it say? 1 minute later, the positions have changed, and that's how far they've changed. Okay. All right, now give the linear equation for each ship's path. We want it in the form of y equals mx plus b. And remember, m is your slope, b would be your y-intercept. And let me see how they do this. Yep. So our rate of change, we're going up 2, that's our rise, and we're going over 3. And some of you are like, why is it negative? That's for Helsinki, right? No. Yeah, for Andor. Sorry, that was for Andor. So, yes, I know that we have these arrow points going this way, but if you're looking on the graph and if you're reading the graph, you're starting on the left and moving to the right. And as you do that, you're actually decreasing here. So we would say that we're decreasing, even though, yes, this ship is pointed that way. Let me go, yeah, all right. So our rate of change was, we're going up 2 and to the left 3, because we're going left, it's negative. And then we're multiplying that by x minus 900. And some of you are like, wait, where's the negative 100 or 900, excuse me. And that's basically, we're getting that from your basic formula for your basic linear equation is y equals x. Let me move this way. Y equals x. And so if we were here with our basic equation and we transformed that by shifting it to the right 900, then the transformation on your linear equation would be x minus 900, and that would be in parentheses. Okay? Hopefully you have not forgotten about all your transformations. And then where are they getting the 0? Oh, the transformations, yes. We are not moving it up or down at all, so your x-intercept is when y is 0, so we're just not moving it up or down. Okay, so we get that. And then, of course, we always want to distribute anything to get rid of the parentheses. So we notice this equation, mx plus b, does not have any parentheses in it. So we want to get rid of those parentheses. So we're going to distribute the negative 2/3 throughout the equation. And when we do that, we get negative 2/3 times x plus 600. Those of you trying to figure out where the 600 came from. Notice you have a negative here and a negative here. Negative times a negative gives you a positive, and 2 divided by 3 times 900 gives you 600. Okay, so that's how we found the linear equation for the Andor. Now for the linear equation of the Helsinki, this one's a little bit easier. Let's look at our graph again. Our y-intercept is at 100 because we know that because the word problem gave it to us. And then we also know that the slope is we're going up 1 and over 4, and it's a positive slope. So it's going to be y equals 1/4 x plus 100 because our y-intercept is at 100. Okay, so there's our linear equations for both of those ships. Okay, and then so notice I have starting points here, and I have, if this was a vector problem, these would point to where we stopped or where the ship stops. Now, we aren't studying vectors here, we're studying parametric functions, and so your point here is still going to be where your equation starts, but unless in the word problem says the ships only sail for 5 minutes or whatever, then the arrow points just indicate the direction that they're going and that they will keep on going. This is not an end value here. If it was an end value, I would put a dot here and I would put maybe the arrow points here to show that the ship is sailing this way. Okay? All right, so problem number 3. How many millimeters east and north of the lower left-hand corner of the screen did the paths of the ships cross? So we want to know where exactly, let me change colors and shapes. We want to know where this spot right here is. Now, most of you can tell that it's approximately, it's a little bit more than 500, and it's a little bit more, your y value would be a little bit more than 200. But you know me, I do not want approximate answers. I want the exact answer. And to do that, we're going to take the two equations that we got from problem 2C, these two equations, and we're going to set them equal to each other. I want to know what is the x value when both of those equations will be equal to each other. Okay, so we're just taking the equations and setting them equal to each other. There's your two equations. And then we're going to solve for x. I want x to be by itself. Okay, to do that, I'm going to subtract by 100 over here, and then I'm going to add 2/3 of x over here. Okay, when we simplify, we get 500 equals, whoops, pretend I didn't uncover that. We'll get 500 equals all of this here. Now, most of you know that you cannot just add your fractions. You have to have common denominators. And so both fractions will have to have a denominator of 12. So this will become 3/12 over x, or times x, plus 8/12 times x. Then we're going to add those two fractions together. And we get 500 equals 11/12 times x. Now, to get x by itself, I'm going to multiply by 12 and divide by 11. And when I put that in the calculator tells me that my x value is 545.455. Okay. Now, I'm going to take this x value and plug it in either this equation or this equation to find out what my y value is. I randomly chose this equation, but you could choose either one. Okay, so when I plug x in I think I chose this equation. Let me see. Yep, I chose that equation. Okay, so I'm going to plug 545.455 in for x up here. And I'm just going to put that whole thing in my calculator. And when I push enter in the calculator, I get y equals 236.364. So the coordinates of when those two ships will intersect are going to be your x value and your y value. And if you remember, this origin is at the lower right corner of the screen. So you're going to go east and you're going to go north. And you're going to go, whatever your x value is, that's how far east you're going to go. Whatever your y value is, that's how far north you're going to go. Okay. And let me see. Problem number 5. Express regularity in repeated reasoning. Most of you probably realized I skipped problem 4. It's because I think the textbook put the questions out of order. So we are going to get to problem 4. We're just going to skip it for now. We will come back to it. Okay. The instructions here say to fill in the tables below to indicate the position of the ships relative to the lower left corner of the screen at any given time. Okay, so what we're going to look at first is what's happening to your x values as time keeps counting. Okay, so now if you remember the Andor, let's see now. Need to go all the way back to the front. All right, so the Andor, for the first second, it's moved 3 millimeters west. Okay, and we started. Where did we start at? We started at 900, and after 1 minute, we went to the left 3 millimeters. So 900 minus 3 is 897. And then after the next minute, we're going to keep on going to the left. So we'll subtract by 3 again, and we'll get 894. And then the next minute, we're going to subtract by 3 again, and we're going to get 891. Okay, Now, before we figure out where we're at after 10 seconds, let's figure out what the equation is. So for every single second that goes by, I'm subtracting by 3. And my initial starting position was 900. So the equation would be 900 minus 3, because we're subtracting by 3 every single second, times t. Okay, that's how I get the equation for what's happening to the x value. So now if I want to know where am I at after 10 seconds, I'm going to do 3 times 10, which will give me 30, which means that 900 minus 30 will give me 870. Okay? Hopefully I didn't go too fast through this. If you need to, ask this sub to pause it and rewind it, and you can listen to the explanation again. All right, let's look at the y values. Okay, so let's go all the way back there. Now, for every second, the Andor is moving north 2 millimeters. And where are we at? There we are. And we are starting at 0. Okay, and then since we're moving north, we're going to be adding 2 every single second. So after 1 second, we'll be at 2. After 2 seconds, we'll be at 4, and then 6. Okay, so we're adding 2 every single time. We're starting at 0, and I don't need to do 0 plus 2x. It's, well, don't we love the textbook? Okay, so the textbook is telling us that we're starting at 0, and then we're just adding 2 times what my t value is. Do you have to put the 0? No. You can just do 2 times t. Okay? So after 10 seconds, how far north are we? 2 times 10 is 20. So the answer here would be 20. Okay? You're going to do the same process with the Helsinkie. You're going to figure out how far east are you moving every second, and where your starting point is. And initially with our starting point with Helsinkie, we were at the origin, so we were at 0, and I think we were moving 4, right? Yep. For every second, you're moving 4 to the right, and so first you would have 4, then 8, then 12, okay? And so because you're adding 4, it's just going to be 4 times t, and yes, I'm pretty sure the textbook, yep, they did it. They added the 0 there. You don't have to put 0 plus 4t. You can just do 4t. So after 10 seconds, it'll be 4 times 10. So it'll be your eastern or your horizontal location would be at 40 millimeters. Okay, your vertical location, you started off at 100. So when time was 0, you were at 100. And then I think they were going up by 1. So it'd be 101, 102, 103. Most of you have probably already figured out that this final answer would be 110. And then the equation is just 100 plus t, whatever your time is. Okay. So now that we've done this process, let's go ahead and figure out what the formulas are. So for problem 6, we're just going to use these formulas down here, except we're not using the 0 plus. Okay. You're using that formula. So for Andor, your x equation was just 900 minus 3t. And then your y equation was just 2t. Okay, notice how they're showing you that you don't have to include the 0 there. I'm sure you guys are so surprised. Okay, and then for the Helsinkie, it was just 4t. And then the y value was just 100 plus t. Okay, so now let's go ahead and answer the fourth question. So the fourth question is, do you think the ships will collide? Clearly explain your reasoning used to arrive at the answer. So this is the same situation as the cheetah. There's 3 options. Number 1, Andor will get to the location first, and then it will keep on going, and the ships will miss each other. The other situation is that Helsinkie will get to the location first, and then it will keep on going, and then they won't collide. Or the third situation is they both get to the same location at the same time, and then there's a crash, and people are drowning, well, falling in the ocean. Hopefully they have a life jacket. Let's think positively, and they have a life jacket on. All right, so let's figure out what's going to happen to this. To figure that out, we're going to graph these equations in our calculator. Okay. To do that, you're going to pull up your calculator. You're going to go to the graphing screen. Make sure if there's anything here, go ahead and clear it. Push Dock B to clear the calculator. And then go back to the graphing screen. To get the parametric functions, you have to go to Menu, Graph, and then Parametric. Okay, so you can see here how you have a slot for your X formula and a slot for your Y formula. And I totally forgot what the equation is. Let me move this over a little bit and make room for this. There we go. So the first one, I'm going to graph the Andor. So I'm going to have 900 minus 3t. Notice I am using the t here, not the x. Do you see how you have a t in the parentheses here? And then for the y value, it's just 2 times t. And I'm going to push enter. Now, I know you guys can't see it. Let me graph the second one, and then we'll change our window for this. Okay, so now this time, because we already put one parametric function in there, all we have to do to pull up the equation again is just push tab. Okay, and let's go ahead and graph this one. For Helsinki, it's going to be 4t, and then 100 plus t. Okay, push enter, and again, we don't see anything. We will have to change our window. If you go back to this screen, it shows you what your window should be. So let's go ahead and let me change it this way up so I can see the whole thing. I'm going to go to Menu, Window Settings. My X minimum can probably be, I want to see a little bit more over here. So I'm probably going to do my X minimum of negative 100. My X maximum of 1000. Let me check and make sure I have all, oh, too many zeros. So negative 100, 1000. Don't leave this at auto. Change it to an X scale of 100. And then let's see, your Y minimum, same thing, negative 100 here. And notice they only go up to 800 here. So your maximum Y max of 800, and again the auto or the scale of 100. All right, push enter. Oh yeah, I forgot. Last thing I was going to tell you about this. So notice you have this here, and you only have this itty bitty tiny spot here. And then you have the other formula over here, and again, you only have this itty bitty tiny spot. Okay. What you have down here tells you how long or how many seconds of data you're going to record. So this is only telling you the data from 0 seconds to 6 seconds. If we wanted to know, actually these are minutes, right? Yeah, the situation was after every minute. So this is only 6 minutes of the time. Let's say we wanted to know the first hour of time. All we would do is come through here and change this to a 60. Okay? And still you only get this short segment here. So let's say, I don't know, 600 minutes. Okay, so 600 minutes actually shows me this full line all the way across the screen. Okay, so I'm going to do the same thing with the next formula. I'm going to change this from 6 minutes to 600 minutes. And again, it'll show me all the way through the screen. Okay, now notice we have, it shows you the intersection. And I'm not sure if we can actually analyze the graph. I've never tried analyzing the graph with these. Let me see. Yep, see they don't. So parametric functions are one of those weird ones. You can graph it, but you can't use the analyze graph feature. See, I'm actually clicking on this and it will not select the graphs. Okay, so unfortunately, you can't have the calculator do all the work for you, but we can check and see if, let me see if the trace works. I'm pretty sure graph trace, yep. So it actually starts off right here. Okay. They're showing, it starts on the intersection where the approximate intersection. So I want to know, what is my time? All right, so I'm pulling up my table and it tells me the initial location, the initial x value, the initial y value, when time is 0. And I want to know, when does the blue graph, this line, get to 558? And when does the red graph get to 558? So I'm going to scroll down and notice the blue graph is decreasing in amounts. And I'm scrolling down and scrolling down and scrolling. Whoop, I passed. No, I didn't pass 548. There we go. So somewhere after 117 seconds, I'm eventually going to get to have the x value of 548 and approximately 237. Okay, but the red ship is not anywhere close to it. It's only at 468 and 217 seconds is the y value. So they're not going to be at the same place at the same time. It doesn't matter, to me, it doesn't matter which ship gets there first, as long as they're not both there at the same time. So the question that we originally started, let's go here. Do you think the ships will collide? Yes or no? I don't think so, because they're not at the same place at the same time. Okay, let's see what the textbook says. No, the ships will not arrive at the point of intersection at the same time. Andor will arrive in about 118 minutes, exactly what we found on the calculator. And we didn't actually look for when Helsinki will arrive, but if we notice the Helsinki is going up to 237, approximately 137 seconds, okay? 137.67 minutes, okay? And so they're not going to be at the same place at the same time. So there's no crash. The ships, they just pass in the middle of the night, and everybody's all good. All right, so let's look at the rest of the stuff that you guys have to do. The rest of the problems, I'm not going to help you as much as I did with our ship problem. A lot of these you will have to answer on your own. On any of the ones that have an explanation, I'm going to show you the textbook answer. Sometimes I will have my own explanation as well. So for number 7, it says, make sense of the problems, explain how you determine the speed of the Andor in item 2B. We kind of already went over that. The answer the textbook gives you is this. The Andor starts at 900 and 0. Those are the coordinates. After 1 minute, its new coordinates are this. You can use the distance formula, find the distance of the Andor moved, and that's also the Pythagorean theorem. Okay, and you get the square root of 13, and the Andor moved the square root of 13 millimeters, or about 3.6 millimeters in 1 minute, so that's its speed. Okay, again, Pythagorean theorem, our vectors, we're going over, we're going up, and you can do the square root of 2 squared plus 3 squared, and you get this length, speed here for our vectors. Okay. Problem 8, why might it be useful to know the ship's horizontal and vertical positions as functions of time? Your textbook answer, I actually like this textbook answer. Go ahead and write it down. If you need the teacher to pause the video so you can get it all written down, ask her to do so. Okay, so the textbook answer, if you can determine the positions of the ships over time, you can determine whether the ships will ever have the same position at the same time. In other words, you can determine whether the ships will collide. and whether everybody drowns, or terrible, horrible death, or if everybody keeps on partying on the ships. Okay, that's my answer. All right, number 9, determine the position of the Andor at time of 20 minutes. Explain how you determined your answer and how you know that your answer is reasonable. I have my answer, and the textbook has their answer. I think the actual answer is these coordinates. So after 20 minutes, you're at 840 millimeters east and 40 millimeters north. And there's this big, long explanation in the textbook. You evaluated the function for you plugged in t 20 minutes for t to find the x coordinate of the ship's location, and you did all that math for the y coordinates and eventually got that as the solution. And then you could have also plugged that into your linear equation, which models the path of the Andor. Okay, so big long explanation. My answer: you graph the parametric functions, you pull up the table, and find your answer. Okay, so if we wanted to know where the Andor was, we would just pull up our graph and go scroll all the way up until your time is 20. Eventually we'll get there. There we go. And there's your x value. There's your y value of, actually, whoops. That was the x value and y value of Helsinkie, I think. There's your x value and y value of, what was the other ship? Andor. So we actually, a lot less work if you graph it and have the calculator do all the work for you. I know I'm probably a horrible math teacher to say that, but with all the calculations you have to do in pre-cal, any calculation that you can avoid doing is all right by me. All right, so let's look at the other problems. Another problem situation. This one you're going to do a lot on your own. Let me move this out of the way for now. In a video game, a player earns bonus points for each spider his or her character catches. A player moves from the coordinate point 30, 24 to 65, 59 on the screen in 1 second. At the same time, the spider moves from coordinates of 20 and 315 to 100 and 255. Assume the player and the spider will continue to move at a constant speed along the linear path. Remember, anytime you see the words constant speeds and linear path means you're going to have a linear function. Sketch, so for problem 10, sketch the path of the player and the spider, write the linear equations that model the path. Okay, most of you, in fact, all of you will need to get your own piece of paper out. You're going to want to set up a table, or excuse me, a graphing screen like this. In fact, your calculator, if you want to do it on the calculator first and then draw it on your paper, that's fine too. You want to go from, let's see, negative 50, your x minimum is negative 50, to 500, a scale of 50, have tick marks every 50, and then same thing for your y value, negative 50 for your minimum, positive 500 for your maximum, and tick marks or grid lines every 50 units, okay? This is what your scale is going to be. Now let's look at actually plotting points and everything on your scale. So notice we start off with the player. My green line is my player. Then start approximately right here. I'm not going to take a millimeter to your work and make sure it's all graphed exactly perfect. So approximately right here, I'm going over and up to here. And then the spider starting way over here and going down into the right to right here. If I take your ID, draw a line connecting the dots, and you'll see the path that it's going to take, okay? And then, do we ever write linear equations that model the paths? That one, I'm going to let you guys figure out how to do that one, okay? Find your slope by doing the whole rate of change. You know, your 59 minus 24 gives you your rise. 65 minus 30 gives you your run. Same thing down here to find your rise and your run. For the spider, you're going to have a negative slope. For the player, you'll have a positive one. Okay, and then you just need to find your your y-intercept. Okay, I'll let you figure out that one. If you don't remember how to do it, look it up on your phones. And yes, I am giving you permission to pull out your phone really quickly to look up how to find your y-intercept. Okay, it's super easy. You learned how to do it in Algebra 1. If you don't remember how to do it, go to YouTube. I'm pretty sure there's lots of Algebra 1 teachers that have posted videos on how to find this y-intercept. Okay, all right. Next question, what are the coordinates of the point of intersection of the path of the player and the spider? Okay, I'm going to show you the instructions on how to do it, and then you need to do it. I think on this one, let me see. Yeah, I do show you your answer. Okay, so the first thing you want to do, the two equations that you got from here, you're going to find both equations. Then you're going to set the equations equal to each other. Then you're going to solve for x. Then you're going to plug in your x value into one of the equations, and you're going to solve for y. Okay, if you do all of your work correctly, your answer should be, your x value should be 192, and your y value should be 186. Now, all of you that are busy copying down the answers and you don't do anything else, I am not giving you credit if you give me, if all you have is this answer. I want to see your work. Show me your work. Show me how you got that answer. All right, so determine the speed of both the player and the spider in units per second, round to the nearest whole number. This one, remember our vectors and how we, excuse me, let me do a line again. All right, so remember our players and our vectors. If we're going one direction and then another direction, we can draw this straight line, and you have a right angle here. Pretend that is a right angle. Okay, you can do the Pythagorean theorem, use your vectors, find this length here, and in this case it's going to end up being speed. Your magnitude will end up being the speed. Do that for both the player and the spider, combine their speed. Okay, and then make tables of the values to show the horizontal position and the vertical position of the player and the spider. Make sure you are setting up two different tables, one for the player, one for the spider. Make sure you have your t value from 0 to 5 seconds, your x value and your y value for both tables, okay? And just same thing that we did way back where, right here. Set them up exactly like this, your player, x, y. Figure out what is changing every second for your x values, figure out what's changing every second for your y value, and then you should be able to figure out your equations here. Okay, and then see, that's for 13 is the tables. For 14, write rules for x and t, x of t and y of t to model the horizontal and vertical positions of the player and the spider for the function of time. If you set up your table here, you'll be able to figure out what the x value is, and you'll be able to figure out the y value for both the player and the spider. All right, so I want you to get all of that done. Anything you don't get done in class is going to be homework. If you need the teacher to rewind the video, let her know. Ask politely, and I will see you guys on Tuesday. Bye.